Hi, I'm thrilled to have with us today Professor Fanglin Che. Fanglin did a postdoc in our group, but before that, she did her undergraduate studies at Dalian University of Technology. She did her PhD in Washington State University in Chemie, working with Professor Jean-Sabin McEwen. She then came to the University of Toronto, which is where our group was based at the time, for a first postdoc, and did an added brief postdoc with Professor Dion Vlachos at the University of Delaware, also in Chemie. Now Fanglin is a faculty member in Chemie at Umass Lowell, and we're very pleased to have her with us today.
Thank you.
I'm joined in the interviewing by Dr. Jiaqi Yu. Jiaqi is a postdoctoral fellow with us at Northwestern University, and she's going to take over the interview in a moment. Jiaqi completed her PhD in chemistry at Iowa State University, where she worked with Professor Wenyu Wang. And over to you, Jiaqi, to lead today's discussion.
Thank you, Ted. Hi, Fanglin. Nice to meet you. Would you like to start with a brief introduction of your own research group and your own research?
I can share my slides and talk about our research. This is my research lab in chemical engineering department at the Umass Lowell. If you see the keywords highlighted in blue, our lab is mainly doing multi-skill and multi-physics modeling combined with machine learning for catalysis, solar cells, and with the concept of sustainability and the renewable energy, fuel, power generation, and storage. And if you see from different pictures I highlight in these slides, we are working on different perspectives. We are working on electrocatalysis, including carbon capture and conversions. We also work on plasma catalysis for hydrogen generation, storage, and utilizations. Combined with the machine learning, we can scan our material to be and operations faster for the sustainability purpose. And then we also working on different renewable technologies such as microwave heating, joule heating, which can enhance the energy efficiency of the industrial heating. All of our perspective are using computational data-driven technologies. This is basically an overall picture of the lab.
It's amazing. You're doing so much great work in the machine learning, the computational research. Following by this, would you like to share with us some of your previous experience? Basically, what's your academic journey that lead you to this amazing group that comprehends with lots of different acknowledgement, lots of different skills? Like basically, what do you do for your graduate, for your postdoc, and how did you manage to do so much researches in one single group?
Thank you for the question. So I will go to the slides related to my graduate study and the postdoc study. Yeah, so I will start from my graduate life. So I was doing my PhD life in Washington State University. We were investigating the electric field effects at the interface between the anode and the electrode, at the interface of fuel cell. And what we found is that with the electric field at the double layer, that will significantly reduce the coke formation and promote the methane conversions. So that was my thesis work. Then from that time, I realized this electric field concept is very important to tune the catalysis rather than just the temperatures. And that was with the collaboration with Professor Suha and Dr. Jake Gray. So during the postdoc work with Professor Sargent, first project I was working on is the electrocatalysis. It's also experimental and theoretical collaborations. What we look at is basically a subsurface chemistry for CC couplings. And I believe we were the first team quantitatively looking at basically what is the best energetics for the CO binding energy on the surface for the CC couplings. And we found that basically there is an optimal range for the CC coupling. And also you are not just looking at the average, you also need to see the difference between these two COs on the surface and how the subsurface will tune the CO binding energies for the electrocatalysis of CO2 to ethylene and ethanol. So the second project I took on is basically trying to see basically the structure sensitivity of the catalyst to the CO2 going to different products. And what we found is that when the structure got restructuralized, and when you have different coordination number, it will lead to different productivity of your products. And then if you see my second postdoc work, I was looking at microwave heating, and I was looking at basically computational fluid dynamics. And what from there, I can show you one of the videos here. I actually inspired from these videos in the YouTube and the Peanuts paper. So this is basically a cutting grape inside the microwave. And you can see that after we have this cutting grape inside the microwave, it starts to be flaming. It starts to have the plasma generate from this microwave. And that inspired me. When you have this microwave going on, when you have the touching particles, you will have super strong electromagnetic field. And that actually consistent with my electric field concept. And also that inspired me that plasma can also lead to different perspective of the catalysis. That is basically the fourth party of what you can tune. Then that inspired of my Navy project that plasma is another way. Instead of tuning the electric field, instead of tuning the temperature, I can also use plasma to tune my catalysis. So all the work from the postdoc, from the PhD inspired whatever the concept I generate in my own group. I hope that answered your questions.
When you were preparing to compete for an independent faculty position, how did you come up with a proposal for what you would do as an independent PI that was original, that was different from what your previous advisors had worked on, but that took advantage of the learnings that you'd had in your previous group?
Okay, great. So I think inspired from, let's say, the PhD work, of course, I want to be independent. So I learned about electric field effect is very important for my PhD work on catalysis. But majority of the work you're doing there is flat surface. So on the flat surface, we know that you need to input a huge amount of the electric field, which is basically already breaking the air. But it's really, the question is, really you need that huge electric field to generate some field effect for catalysis. Then during my postdoc work with TIDE, I learned about structure sensitivity is very important for catalysis. And I also learned from the instruments such as STM, we know that we need to have this kind of needle shape in order to generate really high electric field. So combine these two studies, we know that electric field, you need to have huge electric field to have field enhanced catalysis. The second part, you need to have this high curvature. You need to have defects of your surface in order to generate this huge field. Then I've combined them together to generate my new idea that you need to have basically the particle involved in your simulation in order to count the field enhanced effect. And also from the past, we always doing DFT, and we know that DFT is very slow. So can we use deep learning? Can we use machine learning trying to accelerate the DFT calculation so that it can fast testing your hypothesis, fast generating the result? So that is merging them together that formulates my DOE early career proposals. It's always combined with whatever I learned, but it's very different with what we already done in the past group. So that is the central of the proposal formulation.
Great. Thanks, Fanglin. Well, it's been wonderful to have you with us today. Thank you to Professor Fanglin Che of Umass Lowell for joining us for today's discussion. And thank you for Dr. Jetshi Yu for having facilitated today's interview. I really enjoyed hearing from both of you today.
Thank you.